Okay, we start section 14.2, double integrals in polar coordinate. Okay, first theorem tells us that let f be a continuous function on a polar rectangular region D, given by this and this, when theta is between alpha and beta, where beta minus alpha is in between 0 and 2 pi. Then this double integral can be written in this way, as r dr d theta, or this way, r d theta dr. Okay, here this rectangular region can be written in this way by coordinate, polar coordinate. Let's see. Find the double integral 3x plus 8y squared dA, where d is given like this. Okay, then this can be from the theorem. This can be written in this way by the change of variables from rectangular coordinate to the polar coordinate. Here x is replaced by r cosine theta, and y was replaced by r sine theta, and dA was replaced by r dr d theta. So if we do the integration, then it gives us the value 7 plus 15 over 2 pi, like this. Okay. So now this rectangular region can be written as can be drawn as a polar coordinate like this. Okay. And this substitution naturally gives us the answer like that. Okay, the second example. Do the integration of x squared plus y squared to the 3 over 2. Divide the x from here to here by transforming this to polar coordinate. This polar coordinate. Okay. Okay, as you see, this integral can be rewritten as a x can be replaced by r cosine theta, y can be represented by r cosine theta, and this can be replaced by r dr d theta. Okay, then x squared plus y squared is r squared times what? Cosine theta plus sine theta, which is 1. And so square can be cancelled. We have r cube times r dr d theta. So we have r force dr d theta. But so after that, we need to integrate this with respect to r and theta. So we should change the domain, the domain in terms of the parameter, the polar coordinate. So this region, which is from 0 to square root of 1 minus x squared, and from minus 1 to 1 on x-axis. So this region can be written as in polar coordinate. Here r from 0 to 1 and theta from 0 to pi. So r from 0 to 1 and theta from 0 to pi. So we have this integral, which is very easy. Easy integral to find as a pi over 5. Okay, so sometimes the double integral with respect to the region like this can be more easily obtained by this transforming to the polar coordinate. When you draw the graph, you can utilize this grapher for the parametric equations like this, and you can change the a's and b's, and you can change the functions here for the parametric equations 1 and 2, and also the polar equations can be written in this way. If you wanna see how it changes as time t moves, then this gives you how it is drawn. This is a function of this graph. when t from minus pi to pi. If we extend it to from minus pi to 18 over 4 pi, then we will have this graph. One term and some more, like this. If we change the a as a bigger number, then we will have more leaves. If we have this B11, then we will have more leaves like this. Okay? And so anyway, yeah, we have what? We have implicit functions to draw. And we also have the butterfly, which is this function. If we change a's, then it gives us a different shape. And if we, that is flowers, and what? This gear can be generated by these functions. If we make a more then we have a very small. Now it's very big. I want to make more. Yeah, if we make C bigger, then we have more code. And these kind of the tools can be used to produce such things. And there are more things that we can think of to see the animations. And this function generate the things. Anyway, here I try to show you how the parametric equations can be drawn in it. Anyway, and also this integration can be done like this, so we can find the overlap of these two regions. We can figure out where we're supposed to integrate the regions by showing it. And also, it gives us, if we do the integration on this region of certain function, to have the integrals. Okay. Anyway, so you can use the tools that we have already developed to the double integrals. Next, this is a very well-known Gaussian integrals. Integral from 0 to infinity, e to the minus x squared dx. So how you do integrate? This is a very difficult integration for one variable integration, but it is a very easy integral if we use the double integral. Okay, this integral can be easily found by double integrals. Also, the information related to this integral can be found in variable website on Gaussian integrals. Okay, anyway, this integral, we do integrate this function from here, x is from 0 to infinity. Okay, so so here we let this function as the I, then this value is same as the integral from 0 to infinity to the e to the minus y squared dy. Okay, so if we multiply these two, then by Fubini's theorem, we can write this as a double integral double integral like this. So let's try. Then the tactic is to find this double integral and take the square root of this value to get what we like to have. In this case, if we choose the polar coordinate, then this x square plus y square is transformed to r square, and this dx dy can be translated to r dr d theta. And this region from x from 0 to infinity and y from 0 to infinity represents the first quadrant So from here the theta from 0 to pi over 2, and r from 0 to the infinity. So this I square can be written in this way in the polar coordinate form, and we substitute r squared t, then d2r dr can be written as dt. So we eventually this integral, which is the one and which can be easily obtained, and then this double integral can be written as 1/2 times integral from 0 to 2 pi d theta, which is pi over 4. That gives us this integral I as the square root of pi over 2. And we can get it by integrating exponential minus x square with respect to x from 0 to infinity, and to have the same answers like that. And this is the end of section 14.2, and here is the problems related to the double integrals in polar coordinate. And this gives us the many interesting problems that you can deal with the solutions. So you may solve some of this problem by hand or by Sage and post it in the Math 1. I think that's it for the section 14.3, and we will continue section 14.3.